Hi, pre-calculus honors. These are notes 6.3, day 1. We are going to talk about parametric equations, and we have talked about parametric equations in a previous unit. That was probably more of an introduction. We're going to dig a little deeper now. We're going to be talk about more details. So go ahead and pause the video and read the objectives for the lesson. Okay, so a parametric equation is a type of equation that uses an independent variable called a parameter, and we're going to denote that third parameter by t. Dependent variables are defined as continuous functions of the parameter and are not dependent on another existing variable. Parametric equations are used when x and y are not directly related to each other, but are both related to a third term, the parameter t. So in other words, in the past, we would say y is let's say we had something like this. Y is in terms of x, y depends on x, y is a function of x, but now x and y are both dependent on t. This third parameter. So there are many advantages of parametric equations. Parametric equations are helpful if you want to graph a curve that is not a function. Parametric equations can be used to simulate motion, and parametric equations are helpful when considering the inverse of a relation. So there are many advantages, but those are probably the uses that we're going to talk about in this unit. Okay, so the first thing I want you to do is think about, we're going to do an exploration with GeoGebra. So it's up to you. You can Google GeoGebra parametric equations, or you could just watch what I'm about to do with GeoGebra. So it looks something like this: GeoGebra graphing parametric equations. So again, I'll give you, go ahead and pause the video if you want to go there yourself, or you can just watch what I'm doing. It's up to you. Okay, so first of all, if you recall, when we have parametric equations, you have x and y both depend on this third parameter t. So you need two equations, one for x and one for y in terms of t, to graph one. So this is one parametric equation. We have the x and the y. So we are going to go ahead and graph x equals cosine t, y equals sine t. If you choose animate, we'll see. Notice how it started at the point 1, 0. I'll try that again. And notice my t min was 0. My t max was 6.28. So again, notice what we did here. We had our t was our angle, and we started with 0. We're in radians, and we went from 0 to 2 pi. Okay, so again, let's just keep doing some more examples. The next one I would like you to do, let's let x be t this time, and let's have y be sine t. So before you hit enter or animate, think about what it would look like. Okay, so here goes. All right, I should make this larger. All right, so let's see if we make this a t and I animate. Oh, why the heck did it do that? Let me stop. All right, so I have the x is t and the y is sine t. So notice that we're graphing the sine curve. So this is interesting. So if you remember where I was talking about inverses, if you switch the x's and the y's now, notice that I put the y is t and the x is sine t. That's interesting. Okay, let's do some more. Let's do, how about, let's make x t, and let's make the y t squared. Okay, there we go. So after you type in, you have to hit enter. So that was what I did wrong there. There we go. So if you animate, notice that as t maps from -5 to 5, that means your y is going to be those t values squared. Let's see. So what would happen if I made that a negative t? Notice it looks the same. Very interesting. Okay, so I put a negative t there, but watch when you animate. Do you see how it graphed differently? And I'm not sure why that, this must be a glitch with the program here. But notice I have a negative t, and if I hit animate, notice the t is starting at the opposite of what, so it doesn't start at -5. It would be +5. So here, let's do that one more time. That's kind of interesting. There we go. Now it's stuck there. So again, watch how it graphs the point. Okay, this time I want to make my t, or my x t plus 1 and my y t squared. And again, if you hit animate, do you see how it moved it? That's really interesting. It's plus, and it actually moved it right. And which we're so well trained, right, with the transformations. But notice with parametrics, what you see is what you get. You're actually adding 1 to the x coordinate. So let's go ahead and do t minus 1 and see what happens. Notice you moved left. Very interesting. What would happen if you did t squared minus 2, something like that? Let's try it. See, notice it actually moved down. Very interesting. Okay, so again, transformations, inverses, very interesting. I wonder what would happen. Let's do one more. Let's see what would happen if we, let's see what would happen if I put t squared in the x and t in the y. So notice, and you can animate and see. So very interesting. So again, we could think about inverses, because when we had, let's see, when we had t for x and t squared for y, it was, it looked a little bit different. So, okay, so again, I think that this might help you to consider parametric. Okay, so there's my messy writing, but if you remember, when we had x equals t and y equals t squared, we had a parabola that pointed up, and now when we switch the x's and the y's, now notice that was the inverse. Very interesting. Okay, so we summarize everything right here, the definition of a parametric curve. So the graph of the ordered pairs x, y, x is f of t, and y is g of t. Notice that they're called, this is the functions defined in an interval of t values is a parametric curve. So everything's summarized right there in that blue box. Now we need to talk a little bit more about the parameter interval. Okay, so let's grab our graphing calculator, go to mode. We're going to graph x as cosine t and y as sine t. So let's make sure we're in radian mode. We're in parametric. Let's go ahead and go to y equals and type in cosine for x and sine of t for y. So if I choose graph right now, there we go. I'm going to actually have it start again, just so you could see the order that the points were graphed in. There we go. Nice. Now let's see how I got that to look so good. So if you go to the window, I went from 0 to 2 pi. My t-step, which we're going to talk about in just a minute, I just make it 0.05 for now. And then what I did was I did a zoom square. So I think I started with x's from -2 to +2 and y's from negative. But let me show you what happens. It looked kind of like a football, and I know this is supposed to be a circle because it's a rectangular screen. So for example, if you look, it didn't really look much like a circle. So I squared up the window. So if you choose zoom square, you don't have to. We know it's a circle, but it just looks a little better. There we go. Okay, so let's talk about t-step a little bit. First of all, t-step does not affect the range, only the way the graph is displayed. So let me explain what that means. So when I went to window, I made t-step 0.05, but for example, let's say that I make it 0.0001 or something like that, something really small. Now, when you look at the graph and you might think it's broken, nothing's happening. However, there is something happening. It's just making so many calculations. See how it's starting right over here? It's making so many calculations because you asked it to go from 0 to 2 pi and make a calculation every 0.0001. So it's going very slow. So if you hit on, that'll make it stop. Let's go back to window and let's say, okay, poor calculator, you're working too hard. Let's just make it something like, I don't know, 2. So think about it. It doesn't really have to make very many calculations, but then take a look at the graph. Whoa, okay. So notice it only made what? 1, 2, 3, 3 calculations, so that doesn't look very accurate. So I think if you have a little compromise here, that's why I did 0.05, because again, it wasn't too slow, yet it looked pretty smooth. All right, now let's look at part B. What t-interval will graph a circle? Well, we said 0 to 2 pi. But let's say I wanted to graph only the top half of the circle. Pause the video and see if you can think of a t-interval that will graph the top half of the circle. Go ahead and pause the video now. Did you try t-min is 0 and t-max is pi? Let's see if that worked. Great. What if you would have done 2 pi to 3 pi? Yep, still works. Okay, so now think about part D. What t-interval will graph the left half of a circle? I'm thinking, like that. Give it a try. All right, let's see what I chose. So I have the left half of the circle, and I chose pi over 2 to 3 pi over 2. Okay, part E. What equations will transform the graph right, left, up, and down? So go ahead and just play around with your graphing calculator and see what type of transformations and how you can think of transformations that will affect the graph. Well, can you see that I made the radius 2? Let's see how I did that. If I went to go to y equals, notice that I did a horizontal stretch and a vertical stretch by a factor of 2. And again, we're so well trained when you put a 2 for a horizontal transformation, this is not cutting it in half. You're multiplying the x's by 2. So if I take a look at the graph, notice the radius is now 2. So I could do a horizontal stretch or shrink. I did 2 cos x and 2 sine x. Let's think about how you could move, oops, I didn't want to do that. There we go. Let's see how we could maybe move it up or down or right or left. So if we go to y equals, make sure you finish the parenthesis, because actually in the next unit we'll talk about putting numbers inside inside the parentheses. But for right now, we're not going to do that. We're going to go ahead and maybe, how about subtract 1 or something? There we go. And think about what's going to happen. And then maybe over here, we'll do like a, how about a plus 2 or something like that? Okay, I'm going to make my window a little larger. So go ahead and pause the video and see what happens with transformations where you add or subtract a number. Okay, I made my window a little larger, but I still want it to look like a circle when I'm done. And again, it's a rectangular screen, so I'll do a zoom square. There we go. So take a look at what happened. So notice that I subtracted 1 and I moved left, and I added 2 to the y's and I moved up. Very cool. Okay, so last thing on the graphing calculator, what I'd like you to do is go ahead and do number 11. Type it into the calculator, get a window that you feel comfortable with, and then we're going to use trace. So pause the video and try and do that on your own. Okay, so I decided for window, I just randomly picked -2 to 5 for T min and T max. T step 0.05 sounded good for right now. X min, -5 to 5, Y min, and Y max, again, I just kind of randomly picked those numbers. Let's see what kind of graph we get. Oh, there's a line, there we go. Okay, so let's see what happens when we choose trace. Notice our t value is -2, so our x value will also be -2, and our y value is -8. So again, if you substitute -2 in for t in the y equation, you do get -8. And watch what happens as we move the cursor to the right. So we're changing those t values, and notice how it's affecting your x's and your y's. Okay, so for number 12, I've given you a parametric equation, and I gave you an interval for t. And we're going to, for part A, we're going to make a table. So let's give that a try. So we're going to let t go from -2 to 1. And again, when I say -2 to 1, that also is, for example, -1.5, etc. But let's just pick integers. So we have -2, -1, 0, and 1. So notice x is t plus 1. So I'm going to add 1 to all the t values to get my x value. Then y is t squared plus t. So for the y values, I'm going to take whatever t is, and I'm going to square it, and then I'm going to add t. Okay, so now let's try sketching a graph without using our calculator. So when we sketch a graph now we're going to graph with y depending on x. So we're actually ignoring the t. So we have at -1, we have 2. We have a point at 0, 0. We have a point at 1, 0. We have a point at 2, 2. Now again, you could check this on your calculator. I'm pretty confident, especially with all the examples that we've done, I'm pretty confident that this is a parabola. But again, go ahead and check it on your calculator. So if the important thing here, though, is notice our t interval went from -2 to 1, so we don't put arrows at the end. And again, if you wanted to, you could pick maybe, let's see, so that was when we had a point right here. And again, this is kind of interesting that we have a point right here when t equals -2. This was the point when t equals -1. This was the point when t equals 0. Here's when t equals 1. What if we would have let t equal -1/2? Notice that you would have had a point right here. So that's kind of interesting. You could have done that if you wanted to. Now for the last part, we want to eliminate the parameter. So that means we don't want a t anymore. We want just x's and y's. So look at the equations and pick the equation that would be easiest to get the t by itself. So I would think it would be easiest for you to say that t is x minus 1. So now we could take our y equals t squared plus 2, and everywhere you see a t, replace it with x minus 1. Oops. So now we have y equals x squared minus x, so we eliminated the parameter t. Okay, so if a parametric interval is not specified for x equals f of t and y equals g of t, we assume that the parameter t can take on all values that produce real numbers for x and y. So again, notice for this one, I gave you a specific parametric interval for t. Okay, so let's try this next example. It says eliminate the parameter and identify the graph of the parametric curve. Okay, so go ahead and pause the video and see if you can do that. See if you can have, instead of having x and y in terms of t, if you could have y in terms of x or x in terms of y. Go ahead and pause the video and give it a try. Okay, so when I looked at the equations, I thought it would be easier to take y equals 3t and have t in terms of y. So then when I have x equals t squared minus 2, everywhere I saw a t, I replaced it with y over 3. So we end up with x equals y squared over 9 minus 2. So y squared over 9 equals x plus 2. So y squared equals 9 times the quantity x plus 2. So if you actually think about what this graph looks like, there we go. It looks like something like this. So again, if you would have gone back here to graph it in parametric mode, grab your calculator. But this is something kind of interesting. Let's say that we switch the x's and the y's right now. We find the inverse. Here, I'll get a different color. So if I said x squared equals 9 times y plus 2, very interesting that you would end up with a graph that looks like this. And again, they are inverses of each other. Okay, so let's do this. Let's go back to the beginning. And let's say at the very beginning, I would have said x equals 3t and y equals t squared minus 2. Okay, and if we did the same similar thing to what we just did over there, and if we said y equals x over 3 quantity squared minus 2, notice how we would end up with y plus 2 times 9. Sorry, I actually wanted to stop there and show you that. Notice how we end up with y equals x squared over 9 minus 2. So very interesting to think about how when you have parametric equations and inverses, when you switch the x's and the y's, and again, notice that, so again, parametrics are very helpful when you think about inverses of graphs. Okay, let's take a look at this next one. It says eliminate the parameter and identify the graph of the parametric curve. So again, we graph this on our calculator. We used GeoGebra. Let's just go ahead and think about how we would write this without using parametrics here. So first of all, what would happen if you square x equals 2 cos t? I have x squared equals 4 cosine squared of t. And I'm going to square both sides of the equation, y equals 2 sine t. So we have y squared equals 4 sine squared of t. Now watch what happens if I say I'm going to add x squared and y squared. So that's 4 cosine squared t plus 4 sine squared t. Now watch what happens if we factor out the 4. We know that cosine squared of t plus sine squared of t is 1. So we have x squared plus y squared equals 4, which we know is a circle with a center at the origin and a radius of 4. Okay, we just did an entire unit on vectors, so we can use vectors to find parametric equations of a line. So what we're going to do right now is we're going to just think about, let me give you a visual here. So let's say that we're considering the points -2, 3. We'll call that point A, and we'll call this point B. All right, so what we're going to do, let's call this O. So I put another point P over here, and really the only thing that's interesting about P, I'll make another line here, is that P, there we go, P is on that particular line that goes through A and B. Okay, so if we have vector OP, right? We know that that's vector OA plus AP, and let's think about why. Notice OP is the resultant vector when we do tail to tip OA and OAP. Okay. However, if P is a point on the line that connects A and B, that goes through, I should say, the line that goes through A and B, notice that if we could say that OP is OA plus some parameter T, right? Some scalar times AB. Okay, so let's think about point P is XY. So we have X comma Y, and OA, that's -2 comma 3, and then we have this T, and AB, we could find that we have A and B. Remember, we start with the terminal point, the head minus tail method. To put AB in component form. There we go. So now X comma Y, we could add the X components and the Y components. So our X is -2 plus 5t, and Y is 3 plus 3t. And again, our parameter interval, if we wanted a line, would be all real numbers for a line. So again, this is not the way that you would have to do this. It's just interesting to think about this with vectors. You certainly could have just write an equation of a line through these points, and I'll show you that just now. So again, there is not just one parameterization for this line. Over here, another way you could have done it, found the slope, write an equation. You could again make a parameterization for this line by saying x is t, y is 3/5 t minus 9/5. But again, this was kind of an interesting way to do it with vectors. And now if you think about a line segment, right? If we wanted a line segment, I would not think about our parameter interval as -infinity to +infinity. Think about this. If I let t equal 0, so here we go. If you let t equal 0, x is -2. If you let t equal 0 over here, y is 3. So when t equals 0, that was your initial point, -2 comma 3. If I let t equal 1, we end up with -2 plus 5 and 3 plus 3, which was 3 comma 6, which again was point B. So this is kind of interesting that as your t values it goes from 0 to 1. As t varies between 0 and 1, we pick up every point on that line segment between A and B. So we're going to stop the video right here, and we're going to have a part 2 for this last piece.